The solar system is a hostile place. Earth is under attack from deadly cosmic radiation. Life here is only possible because it's protected by the magnetosphere, an invisible force field that cocoons the planet. But new evidence reveals that this vital shield is weakening. A region above the South Atlantic is experiencing dangerous levels of radiation. Is Earth losing its magnetic shield?
It's not a matter of if the Earth's magnetic field would disappear someday, it's a matter of when.
And what will happen to life if it does? Like a giant umbrella, Earth's magnetosphere shields us from the steady stream of cosmic radiation that fills our solar system. Exposure to this is deadly.
The magnetic field coming out from the Earth makes a big bubble around the Earth, the magnetosphere, that protects us from the most violent actions of the sun.
Many of the charged particles in the solar wind have enough energy so that they would represent a hazard to human beings if they made direct contact with the surface environment.
If you're in the path of this oncoming charged particles zipping out from the sun, if you're not inside some shielding, you're dead.
Without the magnetosphere, all life is vulnerable to these high-energy cosmic particles. They penetrate living tissue and cause severe damage to cells.
As the field becomes weaker and weaker, the effects of space radiation would be felt at lower and lower and progressively lower altitudes. So possibly one outcome of a reduced magnetic shield would be, through increased exposure to radiation, higher rates of cancer among populations.
Radiation causes damage at the most fundamental level. It mutates the blueprint of life, DNA. Earth's magnetosphere is our crucial defense. It's so fundamental to our evolution and continued existence that the race is on to understand why it's changing. Although scientists can peer millions of miles into space, they still can't see the Earth's magnetic field. NASA scientist Dr. Mario Acuna's simple demonstration helps us to visualize its basic structure.
We can use a real bar magnet to visualize what the magnetic field of the Earth may look like. So we're going to put this under this piece of cardboard here, and now we're going to sprinkle slowly some iron filings. In school we all play with iron filings, and we sprinkle them on a bar magnet, and we see these lines that form that go from the north to the south, and that in effect basically describes the rough geometry of the Earth's magnetic field.
So just as iron filings arrange themselves around the north and south poles of a bar magnet, the Earth's magnetic field spurts out like a fountain at the magnetic South Pole. It encircles the entire planet and streams back down into the Earth at the magnetic North Pole. Scientists believe it's generated 3,000 miles beneath our feet, deep within the Earth's interior. From here, it throws out a vast magnetic cocoon that envelops the entire planet. This blocks out the solar wind, a constant barrage of superheated charged particles streaming from the sun at up to 1 million miles per hour. Professor Dan Lathrop from the University of Maryland has seen how powerful the solar wind can be.
Solar wind comes in and hits the bow shock on the magnetosphere, and tends to just go around them, right? The whole thing's shaped kind of like a big tadpole. Most of the radiation then ends up streaming past the Earth. A little bit leaks in and hits the atmosphere near the poles.
In polar regions, where the magnetic field is weakest, auroras glow in the sky. These dazzling displays of colored lights form when solar particles slam into gases in our atmosphere, causing them to glow. The stronger the solar wind, the more dramatic the auroras. Although beautiful, they're a sign of the ferocious battle between our magnetosphere and the invading stream of solar radiation.
There's no magnetic field. Face-on radiation all across the planet.
But scientists have made an alarming discovery. Face-on radiation is hitting Earth. Out here, in the Atlantic Ocean, just off the coast of Brazil, sits a region with a rapidly weakening magnetic field. It's known as the South Atlantic Anomaly. It's around 3 million square miles and growing. Every day, cosmic radiation reaches closer to the Earth's surface. We don't fully understand the origin of this anomaly, but the consequences could be dire. NASA scientists monitor the anomaly's impact on technology.
The combination of the energetic particles found in the South Atlantic anomaly, as well as new particles being injected there by solar storms, have resulted in many total failures of communication spacecraft.
Satellites can be permanently damaged when they pass over the anomaly. Vital instruments on the billion-dollar Hubble Space Telescope have to be shut down for protection when it enters the area. As the magnetic field continues to weaken over the South Atlantic, radiation is reaching increasingly lower altitudes and could start to affect more than just technology. Professor Peter Olsen believes air passengers will be the first at risk.
If you happen to take a long commercial jet flight, you would be flying through regions where the magnetic field is weak, and possibly at that altitude, increased radiation would impact the airplane.
This could disrupt radio communication, leaving pilots and passengers vulnerable. Scientists believe that the South Atlantic anomaly is a sign of a global decline in the magnetic field. Evidence of this comes from a surprising source. Dr. Mimi Hill uses pottery to uncover the secrets of Earth's magnetic past. Ancient pots tell us about our distant ancestors, but they also tell us how our magnetosphere has changed over thousands of years.
I'm very interested in ancient pottery because it's a really good recorder of what the Earth's magnetic field has done at the time when the pot was fired.
Clay contains tiny particles of a magnetic iron-based mineral called magnetite. Normally, these are randomly orientated. When clay is fired at high temperatures, they start to move around.
All the little magnetic minerals will align up with the Earth's magnetic field. When it cools down, it's locked in.
As the clay cools and hardens, these minerals become remagnetized by the Earth's magnetic field, locking in a precise record of the strength of the field at that moment.
What we're doing is we're taking a tiny little core from an ancient pot and put the small core into our microwave arc intensity systems.
Hill measures the magnetite from an ancient pot. She uses this measurement to calculate the exact strength of Earth's magnetic field at the time the pot was fired.
And yes, we would go on to the microwaving.
She compares this to samples taken from several pots over the last 400 years. We know this is dated to about 1640, 1670,
and can tell from the experiment that the magnetic field strength was stronger by about 10%.
Hill's research indicates that our magnetic protection is fading at an alarming rate. Professor Jeremy Blockson believes that it may disappear 10 times sooner than expected.
If we could flip a switch and just turn off the Earth's magnetic field, it would take about 15,000 years to disappear. Based on the rate of decay of the field that we've seen over the last 150 years, it's currently decaying at a rate that would see it disappear in 1,500 years.
Earth's magnetic field is decaying fast. Discovering the consequences for our planet is a top priority. Earth's magnetic field is fading. But what would happen if it disappeared completely? The answer lies on another planet in the solar system.
We're good symmetrical burn on all 6 elements.
In 1996, NASA launched the Mars Global Surveyor. Its mission to unlock the red planet's secrets.
Coming up on Mark 1.
Of all the planets in the solar system, Mars is the most similar to Earth. Both planets are made from the same materials. They each have hard crusts, dense cores, and relatively similar atmospheric chemistry. Scientists believe that as on Earth, water flowed on Mars' surface. But that was billions of years ago. Today, the planet is a frozen desert. To find out why, the orbiting Mars Global Surveyor collects data from the red planet. Professor Ben Weiss uses this data to reconstruct its past.
Unlike the Earth, Mars today does not have a global magnetic field generated in its core. But if you were to walk around the ancient southern highlands of Mars, you'd be walking in many places in fields as strong as the Earth. But they'd be very complicated, almost like spaghetti, pointing in all different directions, not pointing north at all.
The satellite discovers that certain areas of Mars' crust are strongly magnetic.
It's clear from the fact that the Martian crust is strongly magnetized that there must have been a magnetic field on Mars in the past. Because that's the only way we know to magnetize rocks is for them to form in the presence of a magnetic field.
Why did Mars lose its magnetic shield? And what effect did it have on the planet? To find out, scientists need to analyze Mars rock. Mars Global Surveyor didn't stop to take samples, but Weiss has managed to get hold of something extremely rare: Martian meteorites.
We have some rocks from Mars that were naturally transferred to Earth. These are meteorites that were blasted off of Mars by an asteroid or comet impact.
Weiss takes the meteorite sample into a special magnetically shielded chamber. He places it in a superconducting quantum interference device, or SQUID microscope, for analysis.
So the magnetic field of a rock is extremely weak. So in order to do that well, we need to make these measurements in a very weak magnetic field.
This highly sensitive machine measures the exact strength of the rock's magnetism. By analyzing different samples, Weiss builds up a picture of Mars' magnetic field at the very beginning of the planet's existence.
We have actually one rock from Mars that's 4.5 billion years old. And we've actually recently shown, by looking at the intensity of the magnetization record in that rock, that Mars had a magnetic field that was roughly the strength of the Earth today.
Weiss research reveals that in its first 50 million years, Mars had a strong magnetic shield.
It's amazing the diversity of magnetic fields that we see above different samples. Some of them, like this one, this is an ancient rock from Mars that's 4.5 billion years old. You only see tiny little isolated magnetic anomalies with huge areas of non-magnetic rock in between.
Why Mars lost its shield is a mystery, but what happened to the planet as a result is not.
When Mars lost its magnetic field, it lost its shield that was protecting it from the solar wind and from cosmic radiation, and that had consequences for the evolution of its atmosphere.
The weak magnetosphere allows solar wind to strip away Mars's delicate atmosphere. Its oceans vaporize, temperatures plummet, and any primitive life forms die. The loss of the magnetic field has a catastrophic impact on the planet's evolution. Mars becomes the red planet we see today. If Earth's magnetic protection continues to fade, will it suffer the same fate? If it vanishes completely, the planet might end up like Mars.
How have Earth and Mars evolved differently such that Earth still has a field and Mars doesn't? Actually, the problem at the moment is more one of explaining where the energy is coming from that powers the Earth's magnetic field.
To find out exactly how and where our magnetic field is generated, scientists need to explore the Earth's interior. But this isn't easy.
We really don't know a lot of detail about what's happening 2,000 miles down because there's no way to send a probe there.
Since there's no way to probe it directly, scientists study the structure of our planet using one of nature's most powerful phenomena: earthquakes.
So the seismologists, they wait for an earthquake, let's say in Japan, and then they put an array of detectors on the other side of the Earth and look for the sound going through the Earth. And by listening carefully, they can construct a map of what's inside the Earth.
Scientists measure earthquake vibrations called seismic waves. These waves don't travel through the planet in a straight line. Instead, they bend, changing speed and direction when they pass through different materials. By measuring these waves carefully, scientists learn that the Earth must be made up of distinct layers, like an onion. The surface layer, the crust, is made of solid rock, just a few miles thick. Below sits the mantle. It consists of denser semi-liquid rock. 1,800 miles down is the liquid outer core, a churning sea of molten iron and nickel. It surrounds the inner core, a solid iron sphere around the size of our moon that is as hot as the surface of the sun. Scientists believe that the magnetic iron core generates our magnetic field. But how?
People are easily confused by this idea that there's this big solid iron inner core, so thinking it's just a bar magnet, it's just a permanent magnet frozen in that, and that's what causes all the magnetic field. But it's too hot inside the Earth. That can't happen. When the temperature gets hot enough, magnets turn off.
Permanent magnets stop working at 1,200 degrees Fahrenheit. So some other process must be generating Earth's magnetic field. To find out more, Professor Dan Lathrop embarks on a very ambitious experiment. At the University of Maryland, he and his team build a 10-foot mechanical model of the Earth's core.
The thing we want to understand is why some planets generate a magnetic field and why others have no magnetic field. So by building experiments, we could hope to understand the conditions of when it works and when it doesn't. What's the switch? Why sometimes a planet comes alive magnetically and why sometimes they remain dead.
Inside this sphere is a solid iron ball surrounded by 13 tons of churning liquid metal. Lathrop uses molten sodium instead of iron because of its lower melting point.
So we've got a rotating outer sphere, holds liquid sodium. It's meant to mimic the iron in the Earth's core.
Separate motors spin the inner and outer cores to mimic Earth's rotation.
Those drive the outer sphere up to about 4 revolutions per second and the inner core up to about 15 revolutions per second. So let's go give it a spin.
If it succeeds, Lathrop's experiment will advance our understanding of how our magnetic field is generated.
Looks good. Seeing 26 tons of rotating metal and liquid up close and the sound, really had no idea it would be like that. It's rather intense.
As the vast sphere reaches maximum speed, something incredible happens. Huge lines of magnetism arc in and out of the model core.
While we can't see the magnetic fields coming out of the experiment, we can measure them. We can put many different magnetic field sensors and then map out these magnetic field lines coming out, rotating, changing. It's fantastic.
Interactions between the inner and outer core create what's known as a dynamo. This generates a powerful, stable and self-sustaining magnetic field.
This is showing magnetic field patterns, red coming out of the experiment, blue going into the experiment. It's nothing like I imagined it would be.
Lathrop's mechanical core supports the theory that Earth's magnetic field is produced by a geodynamo in its interior. The motion of liquid metal in the outer core is vital to this process. The geodynamo depends on the flow of hot, molten metal in the Earth's core. Does Mars's cold core explain how it lost its magnetic shield? Could the Earth suffer the same fate as Mars?
So cooling is going to continue, and eventually the Earth's solid inner core is going to grow larger and larger and larger. At some point, it may solidify completely, and it's possible that even before it solidifies completely, the Earth's magnetic field will shut off.
Is the South Atlantic anomaly a sign that the Earth's core is cooling? Lathrop doesn't think so.
People think about the Earth's magnetic field as just being north-south, right? You have a compass, it points north. Everything's simple. But if you look carefully on maps, you notice that magnetic north and geographic north are not the same thing. Now that's in part because the magnetic pole is actually in Canada.
The magnetic North Pole is elusive. Whenever explorers look for it, they find it in a different place. Larry Newitt, from the Geological Survey of Canada, charts the movement of the magnetic North Pole as it wanders the icy reaches of northern Canada.
To determine where the magnetic pole is, we can't rely on one single observation. What I try to do is surround the estimated position of the pole, taking as many observations as possible.
This wandering is symptomatic of fluctuations in the geodynamo. In recent decades, scientists have noticed that the pole has been moving faster.
Over much of the past 100 years, it's been around 10 kilometers per year. But since about 1970, it started to accelerate, and now it's moving along at about 40 kilometers per year.
In around 50 years' time, it might reach Siberia. So does the wandering pole's acceleration have any connection with the Earth's weakening magnetic field? Professor Jeremy Bloxham is searching for an answer. He uses the records of early sailors to chart the magnetic North's movement over the past 300 years.
Because of the importance of the magnetic field to navigation, people on trading ships and voyages of exploration back in the 17th century or the 18th century were making very careful, systematic measurements of the magnetic field.
Bloxham feeds the historical data into a computer, which creates an impression of the Earth's magnetic history.
What we have here is an animation that will show us how the field has changed over the 300 years or so since 1690. And in the shades of red and orange, we're showing the strength of the magnetic field as it comes out of the core, and in the shades of blue, the strength of the magnetic field as it goes back into the core.
Over the last 150 years, scientists have measured a 10% decline in the overall strength of the Earth's magnetic field. It's fading 10 times faster than if the geodynamo suddenly stopped. But crucially, parts of the field are behaving differently.
Now, as we get into the beginning of the
20th century, we begin to see the emergence of this blue patch here beneath southern Africa, which then drifts to the west and joins up with this other patch, making a large region at the core mantle boundary where the field is going in the opposite direction from what we would expect.
Bloxham's computer model reveals that at the South Atlantic anomaly, the magnetic field isn't just weaker than anywhere else on the planet, it's actually reversed polarity.
There's a patch on the core in the South Atlantic where things are not pointing as they should be. They're opposite, and that patch is growing.
Where the magnetic field has reversed, lethal cosmic radiation that is normally deflected away from the Earth is getting through. The South Atlantic anomaly stretches over 3 million square miles. It extends over much of South America. Radiation currently reaches the upper atmosphere, so it mostly affects our spacecraft and satellites. But if the anomaly continues to grow at the present rate, one day it will reach us.
What's clear is there is storm brewing, if you will, under the South Atlantic.
The storm is only just beginning. If it grows, our vital protection against solar radiation will shrink. The sun will turn from being our friend to our enemy. If our magnetosphere disappeared, high-energy solar radiation would gradually strip our planet of its atmosphere, water, and life. The stakes are high. To prepare for the future, we need to take a closer look at the past.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start.
July the 20th, 1969. Neil Armstrong is the first man to set foot on the moon. It's one of mankind's greatest achievements.
The Eagle has landed. Roger, Tranquility. We copy you on the ground.
But during the mission, Armstrong and co-pilot Buzz Aldrin see flashes of light inside the darkened Apollo 11 module. Bizarrely, they even see the flashes with their eyes shut. When they return to Earth, they report what they saw. NASA scientists are mystified. 6 years later, they come to believe these light flashes are the result of high-energy, heavy cosmic rays penetrating the spacecraft and the crew members' eyes.
There's protons, electrons, just very, very high-energy, ripped-apart atoms spraying out from the sun. In terms of manned space travel, if you're outside the magnetosphere in a big solar storm, large amounts of radiation passing through your body, dire health consequences.
These particles can become trapped inside a region of the magnetosphere known as the Van Allen belt. They present a real hazard to astronauts. At least 39 astronauts have developed some kind of eye cataract 4 or 5 years after exposure to this dangerous radiation. As our protective magnetic field weakens, the risk to life increases. Professor Gary Glatzmeyer wants to know how much weaker the Earth's magnetosphere is going to get. He creates a remarkable computer model of Earth's magnetic field.
We can't reproduce exactly what the Earth has done in the past or what it's doing right now. What we're trying to do is get the model to simulate something that's qualitatively similar.
Glatzmeyer runs the computer model continually. Each year of real time represents 100,000 years of simulated time. He observes how the magnetic field evolves over the millennia. Around 36,000 years into the simulation, something unusual happens.
After being away for a couple of weeks, I came back and looked at the results and then realized that it had reversed, and it was exciting.
Glatzmeyer's experiment shows that magnetic north and magnetic south switch positions.
This is the surface of the model Earth. This is the surface of the model core.
field is directed inwards here and outwards there. The field is much more complicated on the top of the core. Now they're fighting.
Glatzmeyer's experiment shows that magnetic north and magnetic south switch positions.
This is the surface of the model Earth. This is the surface of the model core. The field is directed inwards here and outwards there. The field is much more complicated on the top of the core. Now the reversal is occurring. The field is now directed outwards there and inwards there.
Glatzmeyer's model shows that the magnetic poles swap places spontaneously due to complex processes within the core.
We're very used to the idea that a compass points somewhere near the North Pole, and hence we can use it for navigation. But there were periods in the past when the compass would have pointed in exactly the opposite direction.
Glatzmeyer's research also suggests that there's a decline in the magnetic field strength before and after these reversals. Does this explain why the magnetic field is currently weakest beneath the South Atlantic? Are the magnetic poles about to reverse?
We've never witnessed a reversal, so we don't really know what it would look like. We could guess. And it would almost surely take the bubble of the magnetosphere and contract it inward, closer to the surface of the Earth.
If this is the start of a magnetic field reversal, our planet will face increasing exposure to cosmic radiation for thousands of years to come. But so far, the random reversal of the Earth's magnetic field has only been seen inside a computer. For concrete evidence, scientists turn their attention to the volcanic islands of Hawaii. Locked inside this ancient lava is a pristine record of Earth's magnetic field stretching back millions of years. Professor Emilio Herrero Bevera is searching for clues to Earth's magnetic past.
One of the reasons why we're coming here is because we're looking at lava flows that are relatively thin. You can see the boundary of this lava flow, and this is the other boundary. From here you see another one, and another one, and another one. All these fantastic sequence of lava flows, we're talking about 300 flows, 400 flows.
Molten lava from these island volcanoes accumulates over millions of years. When the lava flows hit the seawater, they cool rapidly, creating snapshots of Earth's magnetic field strength. By analyzing different samples of lava, Herrero Bevera has built up a picture of how the field has changed since long before humans were around.
They are actually the recorders of the Earth's magnetic field in hundreds of years, thousands of years, and this is what we need actually to know something about the Earth's magnetic field.
Lower layers of rock take Herrero Bevera progressively further back in time. To unlock the information, he takes a sample of the ancient lava. As well as showing how the field strength has changed, the sample will also reveal another vital piece of information. He carefully notes the sample's exact location.
And we're going to measure the magnetization of the sample we collected in the field.
Back at the lab, he analyzes it using a magnetometer. Like pottery, lava contains magnetite. When it cools, particles of magnetite line up with the Earth's magnetic field like tiny compass needles, recording both its strength and its direction. In this sample, the magnetite aligns with today's magnetic north.
This sample was in place in the past 700,000 years when the field was actually characterized by a normal polarity.
But in older samples, they discover something incredible. The magnetic particles point south rather than north. They date back to a time when the magnetic field polarity was the opposite of today's.
There was a reversal actually recorded by these lava flows. I will be actually able to see a sequence of points that are actually defining the behavior or the evolution of the magnetic field from one polarity to the other polarity.
By analyzing thousands of lava samples, geophysicists discover that the Earth's magnetic field has reversed over 18,000 times in the last 20 million years. On either side of these reversals is a long period of dramatically reduced field strength.
During this process of reversal, the magnetic field drops very significantly in intensity. And this happened many, many, many times throughout Earth's history. You know, the Earth is 4.5 billion years old, and I'm saying it happens every few 100,000 years or so.
Years of research reveal that the last reversal occurred 780,000 years ago.
It's easy to understand why there's such an interest in the possibility of a magnetic reversal. The last magnetic reversal occurred more than 750,000 years ago. And so, in a real sense, we're overdue for another. And so the question is not if another reversal will occur, but when.
Many scientists now believe that the South Atlantic anomaly is the start of a global magnetic field reversal. The decay of our magnetic field will accelerate, with serious consequences for life.
The kind of radiation we're talking about is known to damage DNA and RNA and cell structure, and it is a serious cause of cancer incidence.
On Earth, magnetic field reversals are comparatively rare and erratic, but on our nearest star, they occur far more frequently.
Every 11 years, the direction of the sun's magnetic field flips. So the sun's magnetic field oscillates regularly, whereas the Earth has these long periods where the geomagnetic field's direction remains more or less constant, and then it flips suddenly.
Although the sun's magnetic field isn't generated in exactly the same way as the Earth's, scientists still observe it closely.
So you get these very different dynamos operating under the same laws of physics, under little different environments. So by studying both of them and comparing them, we learn more about both possibilities.
During its magnetic cycle, the sun undergoes periodic changes in activity. Every 11 years, it enters solar maximum.
This 11-year cycle of solar activity has peaks where there's lots of solar storms, and right now where the sun's taking a little nappy. But in about 4 years, we're headed back for solar max. Big storms, big disruptions.
In 2012, the sun's activity will peak. For 3 years, the buildup of magnetic energy will generate dark sunspots, an increase in solar flares, and hurricane-force solar winds.
Almost every solar max, there are satellites that are killed. The last solar max destabilized the North American power grid and caused massive blackouts during one of the storms. And these are not small storms and inconsequential.
Earth's magnetic field continues to weaken. Soon, this intense solar bombardment could kill more than just power. The imminent field reversal will have a radical effect on human civilization. But it will also threaten the survival of a number of species. Dr. Richard Holland has discovered that as well as using sonar, bats use the Earth's magnetic field to navigate. Holland wants to know how their navigation will be affected by a reversal of polarity.
We catch bats here in this barn at the Princeton University Field Station, and we subject them to a manipulation of the Earth's magnetic field, or perhaps we disrupt the sensory cells that might be responsible for the detection of the Earth's magnetic field by bats.
Holland places individual bats inside this coil.
And zap the bat.
It delivers a very short, harmless magnetic pulse, which scrambles their internal compass.
And pow, there goes the pulse. So he's been magnetized. And pow, there goes the pulse. So he's been magnetized. Hopefully that should have reversed the polarity of the magnetite in his sensory cells. So now we're going to get out there, release him, see where he goes. We drive them about 20 miles away to the north and release them, and we track them as they try to fly back home.
He's off, okay.
Holland wants to see how the magnetic pulse will affect their ability to navigate home. Bats normally fly back to the barn in around 60 minutes. But what happens to those whose senses have been manipulated?
No, that's it. He's gone. He's gone. He's gone, and he's headed north. So this guy, he's had his polarity reversed, his magnetic compass was screwed up, he's gone in the wrong direction. But eventually he'll correct and he'll get back to the home roost.
It takes the bat several hours to make it back. Holland believes that bats sense Earth's magnetic field lines. So when the magnetic field reverses, it's as if they're navigating with an upside-down map. Inevitably, they go the wrong way.
There's very clear behavioral evidence that animals use the magnetic field for a compass, certainly, and also possibly as a map.
But fluctuations in the magnetic polarity don't just affect bats. For decades, whale beachings mystified scientists. But in the 1980s, biologists noticed a correlation between the location of whale strandings and sudden magnetic anomalies on the sea floor. A weakening magnetic field could cause the leader of a whale pod to misread its internal GPS, leading others into dangerously shallow water.
There is the potential for this to affect animals' ability to locate their position using the magnetic field. The Earth's magnetic field as a mechanism of locating their position on the Earth has been vital for animals throughout the history of life on Earth, and so it's hard to imagine life without the magnetic field.
An absence of the magnetic poles could be disastrous for many species, including us. Earth's magnetic field has reversed thousands of times since its formation 4.5 billion years ago. And scientists now believe that the next reversal is imminent. The race is on to predict exactly when it will occur. In 2010, the European Space Agency will launch SWARM. Its mission is to generate accurate, up-to-the-minute maps of the Earth's magnetosphere and anticipate its future activity. Professor Niels Olsen of the Danish National Space Center is working on the mission.
The new and exciting idea behind SWARM is that we have 3 satellites. We have a higher satellite at an altitude of 530 kilometers, and we have a pair of satellites at an altitude of about 430 kilometers.
These identical satellites are equipped with new generation magnetometers. These will detect minute variations in field strength, as well as identifying any new areas where the poles are reversing.
I think it's amazing that we can take magnetic measurements by satellites flying at a few hundred kilometers and say something about the deep interior of the Earth, how the molten iron moves at a depth of about 3,000 kilometers. Isn't that amazing?
Scientists hope these satellites will help them predict when the magnetic poles are about to switch. They might even save lives.
I think that in the next decade or two, we could develop a science to forecast where the Earth's magnetic field is headed and use that then as a planning tool. Use that as a planning tool for people who fly satellites, as a planning tool for people who fly manned space flight, and develop the technologies necessary to deal with, let's say, an impending reversal.
As the reversal approaches, the decay of our magnetic field will continue, and cosmic radiation will get increasingly close to the Earth's surface.
Life on Earth, although it would be affected adversely in some ways by the drop in intensity of the Earth's field, it's figured out a way to live through these events.
So what should we do to ensure the survival of the human race?
There's very little we can do directly about the geodynamo. It's going to behave the way it wants. But now with satellites, we're able to look at it more closely and maybe make some meaningful forecasts. So at least, as a species, we have the chance to adapt.
Life will change. The Earth will be subjected to more deadly radiation. The only visible sign of Earth's weakening defense will be in the skies.
You will probably find the aurora dappled all across the globe, even in the equatorial regions, in places that we never see aurora.
The magnetosphere has shaped Earth's entire evolution. Without it, life as we know it would not exist. Our planet would be barren. It protects us from the effects of solar storms. Although its polarity has reversed many times over the millennia, mankind has never been around to witness it. All life will be affected by a reversal of Earth's magnetic field. But scientists have yet to discover evidence linking past reversals with mass extinction events. If we adapt, we should survive.